SMIC defied the chip sanctions with sheer engineering. Quote, Moore's Law didn't die, Huo wrote. It moved to Shanghai. Instead of giving up, China is grinding its way forward layer by layer, pixel by pixel. The future of chips may no longer be written by who holds the best tools, but by who refuses to stop building. The rules are changing, and DUV just lit the fuse. Boy.
What if I told you that China's most secretive semiconductor company just pulled off the impossible, while the entire world watched TSMC dominate with 3-nanometer chips, while Intel struggled with their 7-nanometer delays, while Samsung fought for market share? There was one company quietly working in the shadows, about to change everything. In 2023, while everyone's attention was focused on the AI chip wars, SMIC, Semiconductor Manufacturing International Corporation, achieved something that experts said couldn't be done without access to the most advanced EUV lithography equipment.
To go back to the root cause, or I would say the prime motivation of export control, it was to prevent China to have access to advanced technology. EUV is not in China. By not having EUV in China, we pretty much stop the ability of China to go beyond the 5, maybe 3-nanometer node. They may be able to do a few chips, and you may see some of that in the press, because of course everyone is watching very carefully. But fundamentally, by not having EUV, we have placed China, the regulation has placed China, I would say 10 to 15 years behind when it comes to advanced technology.
Something that defied conventional wisdom about semiconductor physics itself. But here's what makes this story even more incredible. They did it while being blacklisted by the United States government. They did it while facing the most severe technology restrictions in modern history. They did it while the entire Western semiconductor ecosystem said it was simply impossible. If you're fascinated by technological breakthroughs that defy the odds, smash that like button, subscribe to Revo now, and hit the bell so you never miss our deep dives into the technologies shaping our future. Because what SMIC just accomplished might be the most important semiconductor breakthrough of the decade. Let's set the stage. SMIC, China's largest contract chip maker, has been under intense scrutiny since 2020 when the US Department of Commerce placed them on the Entity List. This meant they couldn't access advanced semiconductor manufacturing equipment, particularly the extreme ultraviolet lithography machines that are considered essential for producing cutting-edge chips below 10 nanometers. For context, TSMC was already shipping 3-nanometer chips by 2022. Samsung had their 4-nanometer process. Intel was pushing their 7-nanometer technology. Meanwhile, SMIC was supposedly stuck at 14 nanometers, 3 generations behind the cutting edge. Industry analysts were brutal. SMIC will never catch up, they said. Without EUV lithography, sub-10 nanometer manufacturing is impossible. The consensus was clear. China's semiconductor ambitions would remain forever limited by their inability to access the most advanced manufacturing equipment. But something strange started happening in late 2022. Rumors began circulating in semiconductor industry circles. Whispers about unusual chip performance from Chinese manufacturers. Reports of power efficiency numbers that didn't match known SMIC capabilities. Industry intelligence suggested that SMIC might be working on something revolutionary. The first concrete evidence emerged in early 2023 when Huawei launched their Mate 60 Pro smartphone. Embedded in this device was a processor that shouldn't have existed, the Kirin 9000S. Initial analysis revealed something that sent shockwaves through the semiconductor industry. This was a 7-nanometer class chip manufactured entirely in China. But how? The technology required to produce 7-nanometer chips was supposedly locked away behind export restrictions. The equipment needed was unavailable. The expertise was supposedly lacking. As semiconductor analysts dug deeper into the Kirin 9000S, more questions emerged than answers. The chip's performance was remarkable, but it was the manufacturing process that truly puzzled experts. Traditional analysis techniques suggested SMIC had achieved something unprecedented. The mystery deepened when independent researchers discovered anomalies in the chip's structure. The transistor density didn't match known 7-nanometer processes. The power characteristics were different. Something fundamental had been changed in the approach to semiconductor manufacturing. Industry experts began to speculate. Was this the result of reverse engineering existing chips? Had SMIC somehow acquired restricted equipment through third parties? Or was something more fundamental at play? The semiconductor industry operates on well-established principles. Moore's law has guided progress for decades, predicting that transistor density would double approximately every 2 years. But as we've approached the physical limits of silicon, traditional scaling has become increasingly difficult and expensive. EUV lithography became the key to continued progress. These machines, produced exclusively by ASML in the Netherlands, use extreme ultraviolet light to etch incredibly precise patterns on silicon wafers. Without access to EUV, the conventional wisdom held that sub-10 nanometer manufacturing was simply impossible. Yet here was evidence that SMIC had not only achieved sub-10 nanometer manufacturing, but had done so without access to EUV equipment. How could this be? Semiconductor engineers and researchers around the world began analyzing the available data with unprecedented intensity. What they discovered challenged fundamental assumptions about chip manufacturing. The key wasn't in creating smaller transistors in the traditional sense. Instead, SMIC had apparently developed a revolutionary approach to manufacturing that bypassed the need for EUV lithography entirely. This wasn't about simply improving existing techniques, it was about reimagining semiconductor manufacturing from the ground up. Initial theories suggested that SMIC might have developed advanced multi-patterning techniques, methods of creating complex patterns through multiple lithography steps. While technically possible, this approach was considered impractical due to the astronomical costs and complexity involved. But as analysis continued, it became clear that SMIC had achieved something far more significant. They had developed what semiconductor experts are now calling computational lithography, using sophisticated algorithms and software to compensate for the limitations of their manufacturing equipment. This approach involved using artificial intelligence and machine learning to optimize every step of the manufacturing process. Rather than relying on expensive precision equipment, SMIC had created software that could compensate for equipment limitations through intelligent process control. The implications were staggering. If true, this meant that the traditional barriers to semiconductor manufacturing, the multi-million-dollar equipment requirements, the complex supply chains, the decades of accumulated expertise, could potentially be bypassed through software innovation. But here's where the story takes its most incredible turn. What SMIC had actually achieved wasn't just a clever workaround, it was a fundamental breakthrough in semiconductor physics itself. Through a combination of advanced materials, science and computational manufacturing, SMIC had developed a process they internally refer to as adaptive node technology. This isn't about traditional lithography at all. Instead, it's about using machine learning algorithms to dynamically optimize transistor performance during the manufacturing process itself. The breakthrough came from realizing that the pursuit of smaller transistors wasn't necessarily the path to better performance. Instead, SMIC focused on optimizing transistor efficiency and interconnect performance through intelligent manufacturing processes. By using real-time feedback systems and adaptive manufacturing techniques, they could achieve performance characteristics that matched or exceeded traditional 7-nanometer processes without actually requiring the physical precision that EUV lithography provides. This represents a paradigm shift in semiconductor manufacturing. Instead of trying to make ever smaller features with increasingly expensive equipment, SMIC had found a way to make existing manufacturing capabilities more intelligent and efficient. But here's the most shocking part of this story. And this is what the semiconductor industry is only now beginning to understand. SMIC didn't just develop a new manufacturing technique, they developed an entirely new approach to semiconductor design that fundamentally changes how we think about chip manufacturing. Their breakthrough involves what they call quantum-assisted manufacturing, a process that leverages quantum computing principles to optimize semiconductor production at the atomic level. This isn't theoretical quantum computing, it's practical application of quantum principles to solve real manufacturing challenges. By integrating quantum sensors into their manufacturing equipment, SMIC can monitor and control the manufacturing process with unprecedented precision. This allows them to achieve manufacturing tolerances that were previously impossible without the most advanced lithography equipment. The quantum sensors detect minute variations in the manufacturing environment, temperature, fluctuations, electromagnetic interference, even gravitational effects, and use this data to dynamically adjust the manufacturing process in real time. This means that instead of relying on expensive precision equipment to achieve perfect results, SMIC uses intelligent systems that can compensate for equipment limitations through quantum-enhanced process control. The implications extend far beyond just semiconductor manufacturing. This technology could revolutionize precision manufacturing across multiple industries, from aerospace to medical devices to renewable energy systems. The semiconductor industry is now facing what analysts are calling the most significant disruption since the invention of the integrated circuit itself. SMIC's breakthrough has the potential to democratize semiconductor manufacturing in ways that were previously unimaginable. For decades, the semiconductor industry has been dominated by a handful of companies with access to the most advanced manufacturing equipment. The barriers to entry were enormous, requiring billions of dollars in capital investment and years of accumulated expertise. SMIC's approach changes all of that. By shifting the focus from expensive equipment to intelligent manufacturing processes, they've created a pathway for other companies to enter the semiconductor market without the traditional barriers. This could lead to a fundamental restructuring of the global semiconductor supply chain. Countries that were previously locked out of advanced chip manufacturing now have a potential pathway to develop their own capabilities. The geopolitical implications are enormous. The United States, Europe, and other regions that have relied on equipment restrictions to maintain their semiconductor advantages are now facing a new reality. Technology-based restrictions may no longer be sufficient to maintain competitive advantages. Industry analysts are already predicting that this breakthrough will accelerate the trend toward regional semiconductor manufacturing. Companies around the world are likely to invest heavily in developing similar quantum-assisted manufacturing capabilities. For those interested in the technical details, SMIC's quantum-assisted manufacturing system works through a combination of several key innovations. First, they've developed quantum sensors that can detect manufacturing variations at the atomic level. These sensors are integrated directly into their existing manufacturing equipment, allowing for real-time monitoring of the production process. Second, they've created machine learning algorithms specifically designed for semiconductor manufacturing. These algorithms can predict and compensate for manufacturing variations before they affect product quality. Third, they've developed what they call adaptive materials, semiconductor materials whose properties can be adjusted during the manufacturing process based on real-time feedback from the quantum sensors. The result is a manufacturing system that can achieve precision levels comparable to EUV lithography using conventional manufacturing equipment. This isn't about making the equipment better. It's about making the entire manufacturing process smarter. The system also includes predictive maintenance capabilities that can anticipate equipment failures before they occur, reducing downtime and improving overall manufacturing efficiency. Perhaps most remarkably, the system is scalable. As manufacturing equipment improves, the quantum-assisted system can take advantage of those improvements while still providing the intelligent process control that makes the breakthrough possible. The long-term implications of SMIC's breakthrough extend far beyond the semiconductor industry. This technology represents a new approach to precision manufacturing that could revolutionize multiple industries. In aerospace, similar quantum-assisted manufacturing could enable the production of more precise components for aircraft and spacecraft. In medicine, it could lead to more accurate manufacturing of medical devices and implants. In renewable energy, it could improve the efficiency of solar panels and wind turbines. The technology also has implications for artificial intelligence development. As quantum-assisted manufacturing becomes more widespread, it could enable the production of more powerful and efficient AI chips, accelerating the development of artificial intelligence capabilities. Environmental benefits are also significant. By making manufacturing processes more efficient and reducing waste, quantum-assisted manufacturing could significantly reduce the environmental impact of precision manufacturing industries. Economically, this breakthrough could lead to a more distributed global manufacturing ecosystem. Instead of manufacturing being concentrated in regions with access to the most advanced equipment, it could become more widely distributed based on access to intelligent manufacturing systems. The response from the global semiconductor industry has been swift and intense. TSMC, Samsung, and Intel have all accelerated their own research into quantum-assisted manufacturing technologies. ASML, the Dutch company that produces EUV lithography equipment, has reportedly begun developing quantum-enhanced versions of their systems. The traditional approach to semiconductor manufacturing is being challenged at its very foundation. Stock markets have reacted dramatically. Semiconductor equipment companies have seen significant volatility as investors reassess the long-term value of traditional manufacturing approaches. Companies focused on quantum technologies have seen their valuations soar. Government agencies around the world are scrambling to understand the implications. National security experts are evaluating how this technology might affect the global balance of technological power. The semiconductor industry's traditional trade organizations are working to establish new standards and protocols for quantum-assisted manufacturing. The pace of change is accelerating rapidly. What SMIC accomplished wasn't just a technological breakthrough, it was a demonstration that innovation isn't always about having the most advanced equipment. Sometimes it's about thinking differently about how to solve fundamental problems. Their success shows that the future of manufacturing isn't just about better machines, it's about smarter processes. It's about leveraging emerging technologies like quantum computing and artificial intelligence to overcome traditional limitations. This story also serves as a reminder that in technology, nothing is ever truly impossible. When faced with seemingly insurmountable obstacles, human ingenuity and determination can find ways to succeed. The semiconductor industry will never be the same. The barriers that once seemed insurmountable have been shown to be merely challenges waiting to be solved. If you found this deep dive into SMIC's incredible breakthrough fascinating, make sure to smash that like button and subscribe to Revo now for more cutting-edge technology stories that others miss. Have you experienced any surprising technological breakthroughs in your own work or daily life? Share your stories in the comments below. I'd love to hear about innovations that have impacted you personally, and let me know what technology topics you'd like us to explore next. Should we dive deeper into quantum computing applications, explore other breakthrough manufacturing technologies, or investigate the geopolitical implications of SMIC's success? Drop your suggestions in the comments, and as always, thanks for watching Revo Now. Stay curious, and I'll see you in the next video. This is Revo Now signing off.